whose line of action all lies in the same plane and intersect a common point. However, all of the individual vectors might not actually in contact with the common point. Now, in the diagram aside, I have shown a representation of concurrent forces in a single plane x, y. You can see this. There are three planes in this diagram. One is x, o, z, the other is x, o, y, and the other is y, o, z. But today what we're going to discuss is about this single plane, that is xy plane, where all the forces are passing through the same point P. As is mentioned in the definition, the forces might not actually pass from the point, but the line of action of the forces should be the same. Now, what are equilibrium conditions for this? If a system of forces acting on a body keeps the body in the state of rest or in the state of uniform motion, then the system of force is said to be in equilibrium. In mathematical language, we can say that for any representation of force vectors in different directions, the summation of horizontal forces should be 0, the summation of vertical forces should be 0. And the moment acting along that particular force should also be equal to 0. Now, we can see that an example explanation given to the theory I explained right now is here. The coplanar concurrent force is said to be in equilibrium condition if it satisfies two conditions. I have already discussed the conditions. The summation of horizontal forces, that is summation of h, is equal to 0, and summation of v, that is the vertical forces, is equal to 0. Now you can see that there are two force vectors in the diagram adjacent here. We will split this force into two components which will be acting in horizontal and the vertical direction. Similarly, for the other vector force, we are going to split it into two components. One will be the vertical one, the other will be the horizontal one. The algebraic sum of the components of all the forces of the system along two mutually perpendicular directions is 0. A detailed explanation of all this can be achieved in the further part of the video. Now, how do we determine the resultant of this coplanar concurrent force system? A resultant force is a single force and is associated torque obtained by combining a system of forces and torques acting on a rigid body. The defining feature of a resultant force is that it has the same effect on the rigid body as on the other original system of forces. Now let us take an example here in the diagram adjacent. There are two forces, both acting in the horizontal direction. They are concurrent, that is, they are passing through the same point. The line of action of both the forces is passing through the same point, hence they are concurrent. They are coplanar because they lie in the single plane, and they are acting in opposite direction to each other. One force is moving to the right side with a value of 4 Newton. The other one is moving to the left side, that is opposite to the first force, with a value of 2 Newton. The ultimate force which will be acting will be 2 Newton. Since we can achieve this taking a summation of all the forces in the horizontal direction, that is plus 4 minus 2 will be equivalent to 2 Newton. Here you can see a diagram of a car which has different forces acting on it. There is friction, which is shown in red. The driving force of the car is shown in yellow. Weight of the car, which is acting in the downward direction, is shown in green. The reaction force to that of the friction is shown in the blue color, and the purple bar or the purple arrow here represents the air resistance. So these are the different forces acting in different horizontal and vertical direction on any of the object which is moving. If this object is to be equilibrium, the summation of all the horizontal forces should be equivalent to 0. The summation of all the vertical forces should be equivalent to 0. But how do we determine the resultant for this? I have shown you one of the examples in this diagram, but there are several methods to determine the resultant force. So in this chart, we can see a representation of different methods. Basically, methods of resultant of force can be split into two parts. The first one is the analytical methods, the second one is the graphical methods. So, what are the analytical methods? Are parallelogram law of force, resolution of forces, triangle law of forces, and the graphical methods are polygon law of forces and triangle law of forces. Today we are going to discuss only about polygon law of forces since our practical is associated with this law. So what kind of verification are we going to do? We are going to analytically calculate different force system and then we are going to signify that values with a graphical representation. What is law of polygon of forces? It is if a number of forces acting at a point be represented in magnitude and direction by the sides of polygon taken in order, then the resultant of all these forces may be represented in the magnitude and direction by closing the side of the polygon taken in the opposite order. For now, just look at this force system. There are different forces acting in different directions. All are the force vectors. They are concurrent coplanar forces. I will explain you the meaning of this definition as we proceed further with a example of the experimental setup. So we can see that here is a system of forces, concurrent coplanar force system. Diagram is represented here. Similar experimental setup we are going to create. This is the kind of assembly or the board on which this practical is conducted. Initially, this board is placed in a horizontal manner. We keep a spirit level at the center to see that the plate of this table is exactly horizontal to the surface of the earth. Then we attach a ring with different kind of weights and we try to make sure that the ring is in equilibrium condition. That is, it is exactly at the center of this whole board. This board has different dimensions which are represented on the sides. So if we look at the free body diagram of this image, it will look something like this. The ring at the center and different forces acting in different directions. So these forces with the arrangement of pulley will be actually the weight which is applied at this particular end of the pulley. So for example, a weight of 1 kg is applied at this edge of the pulley, then the force acting at this edge will be 1 kg, that is 1 into 9.81 will be equivalent to 9.81 Newton. So 9.81 Newton force will be acting at this edge. If this is 2 Newton of weight, then 2 multiplied by 9.81 will be the total force acting at this edge. This whole assembly later can be represented in this format. F1, F2 and F3 are these three forces represented. If this is the resultant force acting, the force which is exactly acting in the opposite direction of the resultant will be equivalent to the equilibrant. I am explaining you this just for the knowledge so that you understand the experimental setup, the first analytical part of the experiment in a better manner. So this R here represents the resultant of the forces F1 and F2. Moving on to our actual experimental setup, I will explain you one sample reading. For example, the position of pulleys are represented here. We are taking 5 set of pulleys on our board. Here there are 4 set of pulleys represented in the diagram. In actual experiment, let us take 5 set of pulleys. So there will be 5 such ropes. With respect to 0 degrees, we will represent position of the pulleys in degrees. Let us keep the values as 30 degrees, 60 degrees, 120, 210 and 240. You can vary this as per your choice. Later, we will add weight of different values and try to balance the ring at the center. We will try to make sure that with different permutation and combination of weights, this pulley are arranged in such a manner that the ring at the center is in equilibrium condition and is exactly center of the board. So this is the first set of reading what we have achieved. The diagrammatical representation of that will be something like this. This is the top view of the board with degree values of 0 degree, 90, 180 and 270 as you can see on this board. There are different set of readings displayed around. Our first reading was F1 force at 30 degree. Second one was at 60 degree. Third one was at 120 degree. Fourth one was at 210 degree. And the next one was 240 degree. These are the representation of the sample readings, diagrammatical representation of the sample reading what we had taken as per the arrangement considering the pulley and the ring in equilibrium condition. So now we will consider this as a free body diagram of forces as you can see represented with different colors. We resolve each of the force component. The force F1 is resolved into horizontal as well as vertical component with respect to the angle theta. Here this angle theta is 30 degrees. I will explain you the first set of resolution. This force F1 is acting. This force F1. Now here F1 represents the weight acting at 30 degrees. So the weight acting at 30 degrees was 1 kg. So when we convert it into force, it will turn into 9.81 Newton. So this F1 is 9.81 Newton acting at an angle of 30 degrees. So we will resolve it into two components. The horizontal one will be F1 cos theta and the vertical one will be the F1 sin theta. Similarly, we will resolve each of the components of different force vectors. This is F2, F3, F4 and F5. I would like to take your attention to this force F3 where the theta value with respect to 0 degrees is 120 degrees. But while taking the force component, the angle theta is taken with representation of this horizontal line. So here this theta will be 60 degrees, that is this angle which I am showing right now. The angle between the x-axis and the purple line will be the theta considered. Similarly, when we talk about this blue force vector, it will be the angle representation between the horizontal axis, that is xx dash, and the blue force component, so that is 30 degrees. Same goes for the orange force vector, that is Fy. It will be 60 degrees with respect to the horizontal axis, that is xx bar. So this is how we have split or represented the forces. Now coming to the observation table, we have noted down the value of theta, that is at what places the string of the pulley is laid. These are the theta values noted down. We knew the weight of each of the force we knew the weight at each end of the pulley. So we noted down the weight and converted it into Newton, multiplying the weight value into 9.81. We get the force value and these are the values obtained. Now we need to get the resultant analytically and graphically. So let us discuss how analytically we obtained these results. As we have to discuss about the equilibrium condition, first we will make sure that we take out the summation of all the horizontal forces. So summation of Fx, and then we will consider all the forces in the horizontal direction, which is F1 cos 30 plus F2 cos 60 minus F3 cos 60 minus F4 cos 60 minus F5 cos 60. This is what is represented here. We substitute the values as per the observation table what I had seen in the shown in the previous part of the video, and we obtain the overall force which is acting in the horizontal direction, that is summation of Fx, it is minus 7.35 Newton. Similarly, we will take summation in the vertical direction. So summation of Fy, we do the equation framing as similar pattern which was done in the first case, and then substituting the values we get the horizontal force vector equivalent to 12.91 Newton. Now resultant of this two will be under root of Fx square plus under root of Fy square, which is equivalent to 14.85. So this is how we obtained the analytical value as 14.85, what I have shown here in the table. Now this is the analytical part of the calculation. Let's move to the graphical method. What we will do first, we will consider an appropriate scale. This has to be done on a graph paper. So initial, that is the first step. I have mentioned the steps at the adjacent part of the diagram. You can see here. So the first step, we will consider 1 point origin after deciding the scale, and we will represent each of the force vectors in continuation. So this is force F1, F2, F3, F4, F5, as we had seen here. This is F1, F2, F3, F4 and F5. Now I would like to take you to the definition part of law of polygon of forces once again to understand this graphical representation. See this. If a number of forces acting at a point be represented in the magnitude and direction, so now we know the magnitude of all the forces for our experiment. F1, F2, F3, F4, F5 is known to us, and the direction of all the forces is also known to us by the sides of polygon. Now we have tried to make a polygon with continuously adding force one after the other. Then the resultant of all these forces may be represented in the magnitude and direction by closing side of the polygon taken in the opposite order. That is, in this diagram we have expressed all the force vectors as per our reading values and tried to make a polygon, but there was some gap left. So when we connect these 2 points, the vector or the force which is created is acting in the opposite direction of all the forces acting, and will be the resultant of this force of this forces acting on that pulley. So this resultant force, we will measure it on the scale and convert it according to the scale whatever we have considered for the graph. So in this case we obtained the values as 15 Newton. So this is how we calculate analytically the representation of different force vectors, and then we signify that with graphical method. Thank you. Before I end the part of this video, I request you to please comment in the comment section if you understood the video, and please hit the like button if you understood the concept completely. If there are any kind of queries, you can mention in the comment section and you will be answered. Thank you so much.